Hi, do you hear me? Okay, so let's start. I'm Martin, and it's my honor to be here with you, and we really appreciate all the reports you are sending to us. So, I sent my first security report to Google in 2003, and actually, I got no response to it so far, so I'm still waiting for it, but since then, many things have changed. I started to work as contractor for Google a few years later, and now I work for Google for almost 7 years, and I'm involved in the Vulnerability Rewards program from the beginning. We started Vulnerability Rewards program for the Chrome browser in January 2010, and later that year we were thinking if it will be a good idea or not to bring the same program to the web. Can it work? Can we bring the same idea from the web, from the client application to the web? It was not clear at all, but you know the answer for today. It turned out to be a good idea. So, in November 2010, we started our Vulnerability Rewards program for the web, because we believe that security researchers should be rewarded for protecting our users, and they work help keep our users and internet at large as safe as possible. During the years, we increased the reward structure several times, and yesterday, I hope that you know, we increased the top rewards again. So now you can get up to $3,300 for the worst bugs in our VRP. So, I will pass to Karshan. And
Hi, I'm Karshan. I've been working at Google for a little over a year now, and I've been involved in the Vulnerability Rewards program since I joined. Before I was at Google, I was at Matasano Security, which is a small consultancy, where I worked as a security consultant for 2 years. Today, our talk is about a few interesting bugs that we received in our Google VRP last year.
Okay. We received many issues over the year. We took only a few of them somehow interesting. This one is about using open redirects to exploit other issues. We don't consider open redirects itself to be a security vulnerability. Some of the members of the security community argue that open redirects aid phishing because the user may be inclined to trust the mouse hover tooltip and not checking the address bar after once the navigation takes place. However, we also recognize that open redirects might be used to exploit other type of vulnerabilities like cross-site scripting or token disclosure. In this bug, clever chain of open redirectors allowed to exploit cross-site scripting issue in one of our websites. So the following bug was sent to us by Tomasz Bojarski. He is a security researcher from Poland, and his report was very simple. It was just one-line proof of concept URL. So we received this one. After clicking this URL, we saw the alert from the events.google.com site. So it was obvious that Tomasz had indeed found a working cross-site scripting issue in one of our properties. This URL is part of the Google I/O 2015 site, and actually the source code for this site is open source. If you want, you can find it on GitHub. So it was a little easier for him to develop a working exploit. So, the payload embedded multiple URLs, and the last one was pointing out to the external appspot.com domain owned by the reporter. So let's explore each part in detail. Sorry. No. Okay, sorry. On the events.com website, there is the page displaying displaying the photos from the Google I/O even. And these photos are stored on the Picasa photos hosting service. And the information about the photos, their addresses and titles are obtained from the Picasa's XML feed. But because the feed is hosted on the different domain, you cannot read the content because of the same origin policy. And what the team did to solve this hard issue is to develop some sort of workaround. So they wrote a server-side proxy, and this proxy was reading the picasa.google.com feed and then serving it from the same host. So this way the JavaScript on that page can read the content and display the photos. Let's have a look at the server-side code. The code is written in the Go language. I'm not sure if you will be able to read it, but check it. Yeah, it works. So they tried to be secure, as usual. So there was a check to ensure that only the trusted Picasa web URLs can be loaded. So there is error in the code. You can probably quickly spot it. Anyone? Yeah. So it's checking just start of the URL. So it's definitely not enough. Not enough. So it was just checking that the URL starts picasaweb.google.com/data/API. So now he needed to find an open redirector on that domain, the domain picasaweb.google.com. And he was successful. He found one. There is some redirector, but this was not enough because this redirector is not fully open. It redirects only to the Google domains. So, for example, www.google.com. So he needed to find another redirector on that domain. He was also successful because we have a few redirectors on www.google.com domain, and for his exploit chain, he used the redirector which is part of the AMP project, the Accelerated Mobile Pages. So after that, the final redirector chain looked like this. The first part is just to pass the check in the server-side proxy, then directory travels to the root, one hop to the www, and the last hop to his domain. So this is again the proof of concept URL. But it's not all yet, because he had access to the source code. He knew that we were setting the content type header to application JSON, and this was preventing the browser to interpret the content as HTML and to run the JavaScript inside it. But what also he found is that in case there is some error in fetching the content, something like display error message is called, and there is no content type HTTP header at all. So what he did was quite clever. This is the attacker's application on the whoopsboxappspot.com site, and what he did is that he just redirected to the invalid URL with the HTML payload in the host. And what happened? The client in the Ghost interpreter shows the error. It was returned to the Go code, and the following JSON was displayed. So it was just cannot fail to parse the location header. So what happened? There was no content type HTTP header. So the browser interpreted the code as HTML, and the JavaScript was executed. So it was the end, and it was the cross-site scripting on events.google.com site. How we fix this? The fix was simple. We deleted the proxy, and we use just the JSON-P as the transport protocol because the photos are public, so you can use it. And obviously, the idea with the server-side proxy was not needed from the beginning. I'm not know if we are being paid by the line of code, but maybe. Thank you, and the next bug is being presented by Karshan.
Thanks, Martin. All right. So this next bug is in XSS in Google Maps. It was sent to us by reporter Nikolai from Ukraine. He sends us a lot of bugs, a lot of great bugs. This one is no exception. So Nikolai found a really interesting URL parameter to one of these JavaScript sources you see over here called paint_origin. So if you set this URL parameter to this script to a base URL like evil.com, Google Maps will go and then try to fetch all its styles from evil.com. It seems like a really weird feature. Why would we ever have this? But we can get into that a little later. But so these styles are usually images, of the map itself, but they can also be essentially HTML. Like if there's a location of interest, like a restaurant or something, the tile would be HTML. So once you could set this URL parameter in the context of google.com, you essentially had an XSS because you could point it to a website controlled by you, and you host XSS payloads on this /map/vt. And you would have an XSS. Although you need to figure out how you can get this to run on google.com, because if you just include this in your website, it's going to run in the context of your website, right? So iframes to the rescue. You can embed Google Maps. Of course, you must have seen this in a lot of websites use Google Maps, right? And now Nikolai found another really, probably a low severity vulnerability on its own, but chained together it got him the XSS. So you see there's a PB URL parameter here in the iframe. And this contains a bunch of information, including the location and where to show Google Maps first. So like, Ukraine, for example, and then the embedded Google Maps would start at Ukraine, and has a bunch more information like the language. You see en-us over there. And the server-side code would use this URL parameter to figure out what to set the URL parameters of all the scripts in the page. Okay, I guess the laser pointer is kind of dead. So you see the en-us in the script source, the language equals en-us, that basically comes from the PB parameter above. And it turns out we don't properly copy URL parameters. We don't enforce the URL encoding. So there was a URL parameter injection vulnerability here. So all you do is you find that en-us in the iframe URL, add a %26, which is the ampersand character, followed by the paint origin parameter, and that would get copied in nicely to the script source URL, and voila, he had his XSS. So how do we fix this? Okay, so let's talk a little bit more about the paint origin parameter. Why do we allow you to fetch styles from an arbitrary URL? Seems, like not really good idea. It turns out there's a feature of Google Maps called Maps Lite, and it hosted, smaller compressed versions of the images on a separate host. And initially, this was implemented with a URL parameter that said, use Maps Lite equal 1, and then it would use the Maps Lite host. But the team decided to, as a cleanup of the code, to make it more generic so that if we had other versions of maps, we could just specify the base URL, and there was no check of what this URL could be. So the first part of the fix was to remove the paint origin parameter entirely. We don't need it. In fact, Maps Lite doesn't use it anymore either. So that was a simple fix. But the second part of the fix was to properly copy the language parameter from the PB to the language URL parameter elsewhere in the response of the iframe to be URL encoded. So if you put an ampersand, it'll remain URL encoded. You won't get a new URL parameter. All right.
Thank you, Karshan. We love to receive nice bugs because we enjoy working on them. So the next bug is about clickhacking. Clickhacking, you know what clickhacking is, definitely, yeah. The user thinks that he is clicking on something, but he is clicking on something different, and mostly the real thing is hidden in the iframe and not visible for the user. We know how to prevent clickhacking. It's simple. If you have the X-frame options, deny header, then you are safe. So, but we received very nice report about hijacking. So let's explore it. To understand why that worked, it's necessary to mention that it was using the Google App Script. Google App Script is JavaScript-based scripting language which can be used to create applications in Google Docs, forms and sheets, and also with third-party providers, and also build simple web applications. All these applications or scripts are running on the script.google.com site. And of course, we cannot run any HTML and any JavaScript on that page because there are authentication cookies. So there were two approaches how to deal with it. One is that we can sanitize the HTML using the tool we call Kaha, you probably know it. Or the second one is that the code itself is running in the safe iframe domain. The domain is sandboxed, there are no cookies in the domain. So for cross-site scripting, we are safe. As I mentioned, the application is running on the script.google.com site, and because you can have HTML, you can create your own iframe. So on script.google.com, there are some UI elements, some parts of the applications, but all of them are served with the Xframe options deny. So even you create the iframe on the script.google.com, you cannot use it for clickjacking. But when we were reproducing the bug and discussing the impact and doing the variant analysis, we found that we serve the same script also in other domains, like in eight domains. And one domain was drive.google.com, which is the domain where all your files in Google Drive and Docs and Sheets are available. So what we found, that there are many parts of the UI which are served just with Xframe options, same origin. So you have something running on drive.google.com. The top origin is drive.google.com. You have some iframe, and you can include another parts of UI inside the iframe. So you can clickjack it, like delete your file, share it with someone other, like all these issues, steal your photos and things like that. So it was actually very clever because we were thinking that we are safe on the drive.google.com because we have the same origin, and it's not possible to have user-controlled iframe on that host. But we were wrong. What was interesting about this bug was also that when the reporter sent it to us, his first impression was, maybe I will not get any reward. But because we found that it was a really nice bug, we found that it's running on the all drive.google.com, we gave him nice reward, and he was happy, yeah. Like I will be happy too. So yeah, he was happy, and we were happy too because our users are safe now. So how we fix that? Fix was not that difficult. We just we are now just sure that the scripts are running on the script.google.com domain and not the other domains. Okay, thank you, and I will pass to Karshan.
All right. This next bug is something we actually talked about last time at NullCon also, but there's been a recent development, so we're going to go a little more into detail with this one. So this was a shell injection in a feature called Google Cloud Shell. I don't know if you guys are familiar with this, but basically it's a feature that gives you command line access to all your Google Cloud resources like App Engine stuff right from your browser, which is pretty nice because you don't need Linux, you don't need to install the G Cloud tool, and you can just do your development from the browser. Although this does mean that there are JavaScript functions in this page that will just run commands in your Google Cloud Shell VM. All right, and one thing that was going on with Google Cloud Shell is that it would set up a bunch of environment variables for you for convenience. So for example, there was an environment variable named dev shell project ID that would be set to your project ID. And how this would work was basically there was a script that would run at the start with export commands, and it would set all these environment variables up. And this is what the code in JavaScript looked like. It's just taking, it's generating shell commands with string concatenation, which is great. And it turns out, you see the get project ID function, that's just grabbing the project ID from the URL. So you can see how this is going to work. I mean, you just put a semicolon to break out of the export command, and then you can run any command in the Google Cloud Shell VM. So the attack scenario here is I give you a link and you click it and I'm running code in your app engine. This is a pretty cool bug. This was actually reported to us by Venkat, who's sitting right there. Yeah. Yeah, and he got a great reward for this, and we spoke about this last year, but why are we talking about this again? So it turns out this was how we planned to fix it. This is how we planned to fix Venkat's bug. We added this shell coating. Maybe you guys are familiar with this, but basically if you're using like untrusted user input in shell commands, well, it's common to put quotes around them to make sure that you can't break out. Because if you put like a semicolon inside the quotes, you can't put another command. The shell will make sure that that's just one argument. Although you need to make sure that you can't close the quote, right? Because if you can close the quote again, you have shell injection. So what the team tried to do here is they put single quotes around the argument, and then they go through the argument and replace all single quotes with single quotes inside double quotes. It's a little confusing, but this doesn't work at all. And we didn't notice this in the fix either, which was our fault. But basically putting the single quote inside the double quotes actually closes the original single quote. That's all it does. And so there was another way to run commands now. You just put a single quote followed by a double quote, and then you're broken out normally. And so somebody else sent us a report again, and it worked. And we reported this bug twice, in fact, with the same amount. And then we did the right fix. Actually, this time it was me personally who was doing the root cause and variant analysis. The first thing I told the team was, look, all these things that are going into shell commands, they're alphanumeric only. So now we have an additional check that just makes sure they're only alphanumeric, and then we did the coding function right, which is to put the single quote inside double quotes inside single quotes. Shell coding is hard. All right. Next one is one.
Okay, thank you. I hope that you are not here just for the Bancraft code, because it was on the previous slide. No, I'm just kidding. It will be at the end. It was on the first slide. No. Let's continue. So the next bug is about cross-site flashing in YouTube. I don't know if you know what is cross-site flashing. Something like cross-site scripting, but in Flash. So the Flash itself is dead, is being deprecated, and the technology with solid track of security issues. So now, if you want to run Flash inside the Chrome browser, you need to click. So I'm pretty sure that the same what happened to the Java applets is going to happen to Flash, because now we have the technology to replace everything we need, like the HTML5. So, but it's still being used for the ads and for video playback on some places. So we still need to support it. As for the JavaScript, there is something called same origin policy. It works almost the same. The Flash file on one domain cannot read the content from different domain. But there is something so-called the cross-domain policy file, where it's easy to specify from which host the Flash can read and to which host can write, and so it's easy. We have a bunch of such files around properties, around our applications. So one of them is drive.google.com. Actually, it's the same as for the clickjacking. Drive is interesting and important. All your Google Drive files are here. So we have such cross-domain policy file. I don't know if you can read it, but there is one interesting domain which looks ugly, sytimg.com. So the reporter who reported this to us was trying to find some flash file on this domain which might be vulnerable to cross-site flashing. He was successful because the code is written by humans and humans made errors, and you can send bugs to us and we will pay for them. So I think it's nice. So it's cycle, yeah. But why not? So the flash on the domain had the flash of the domain was used in ads and was loading another ads inside, for example, YouTube Flash Player. To make things easier, somehow same as for the maps, there is a parameter to specify what is the base URL for these ads, because it's handy that you can set it in URL. So why not? There was some check that the host is fine, that is safe, but the check was not like robust. Let's say it was just checking that, wow, okay, some characters, and that there is some sort of URL parsing, but not definitely that robust, and checking that the second part is YouTube. So also what is needed to understand this bug is that Flash is replacing the backslash character when he saw it to forward slash character. So in case the researcher set the base YT URL to this one, to the first URL, the check was fine. Okay, I think it's fine. It's our site. It's safe, but it was not loading from the YouTube, but it was loading from the attacker side. So at the end, he had a Flash loaded inside the Flash, hosted on the sytimg domain, and because we have the cross-domain policy file on Drive, he was able to read all your documents, files, which is nice. So how we fix that? We added one line to this check because it's really old code. It's the action Flash script version 2, the code from like 2007 maybe. And the longer term fix is just to get rid of Flash at all. So we won't have similar bugs in future. Thank you.
All right. Another bug with backslashes and forward slashes. So this one is pretty cool, but before we get into the details, you need a little bit of context of how our servers work. So at Google, we have these things called Google front-end servers. And this is the first server you'll hit no matter which Google app you're using. So Gmail, Drive, Photos, everything will hit these Google front-end servers. And a fun trick actually you can check out is like, if you just resolve google.com to an IP and send it a request with the host header to say mail.google.com, you'll actually get Gmail sign-in page as opposed to the Google homepage. In fact, I don't know if you guys heard about this app called Signal. They were recently banned in Egypt. And what they did was they used this trick. They hosted a proxy on appspot.com, which is App Engine, and then they sent their traffic to google.com. So the Egyptian government can't tell the difference between Signal traffic and Google traffic. So if they want to block Signal, they have to block Google. And that's how they bypassed it. But yeah, so this is how these front-end servers work. Now to the proof of concept. By the way, this bug was also sent to us by Tomasz Bojarski, who sends us lots of awesome bugs. So the three URLs you see below are the proof of concept URLs. And so let's just go through what's happening here. So it's just, mail.google.com/evil.appspot.com, which is a domain controlled by the attacker hosted on App Engine. And what would happen if you, when this bug wasn't fixed, what would happen is that if you loaded this, you would get the contents of evil.appspot.com loaded in your browser immediately. This is not a redirect. It's like our servers are proxying this to evil.appspot.com. So your browser thinks you're at mail.google.com, but you're getting content from elsewhere. So obviously this is an XSS. And this is an XSS on every single Google domain, right? So you could XSS everything. Accounts.google.com, voila. But even worse than that, actually, because since the entire request is forwarded to the target domain, you can exfiltrate HTTP-only cookies, because the cookies are sent as well. So it's a pretty awesome bug. The one thing that made it not really critical was that it's only exploitable on Safari. And that's because both Chrome and Firefox will convert backslashes to forward slashes before sending the request to the server. But Safari sends backslashes as they are, so it was, yeah. This is the only way you could get hacked. I don't know, maybe it was intentional. No, I'm just kidding. So the fix was, okay, wait, actually, before you talk about the fix, why does this proxy to evil.appspot.com? It makes no sense, right? Like, I don't even know how Tomasz found this bug. But basically, the code that we had on our Google front-end servers to parse the URL, it was originally written to parse client-side URLs. So as you know, in HTML, for example, if you have double forward slash, then what comes next is the host. So originally, this code worked like that. If it saw double forward slash, the next thing would be the host. But the team figured this out, and they were like, oh no, since now we're running this on the server, we need to fix this. So let's ignore all leading forward slashes. And that works. I mean, it's a really hacky fix, but it works. And then sometime later, the team decided, oh, we want to treat backslashes like forward slashes because all browsers do that. And they put this change at just the perfect place to introduce this vulnerability. So they first get rid of all leading forward slashes, then convert backslashes to forward slashes, and then parse the URL. So what's happening is the front-end server sees // evil.appspot.com, converts the backslash, removes all leading forward slashes, which there are none, and then converts the backslash to a forward slash, and you got // evil.appspot.com, goes to the URL parsing code. The URL parsing code says, oh, this is meant for evil.appspot.com, and proxies your request there. So that's how the bug worked. Since it's a really high severity bug, we immediately fixed it by moving the conversion of backslashes to forward slashes up before the removing of leading forward slashes. And the long-term fix is to not allow URL parsing to set the host at all, because that comes from the host header. Yeah. All right. And this last bug is so this is the last bug of our talk, and it's really cool. It was sent to us by Ramses, one of our top reporters, and it's a combination of lots of bugs and a multi-step exploit, and it ends up with the attacker being able to change the victim's password, victim's Google password. And specifically, it's using the account recovery process at Google, which you guys must be familiar with. So let's talk about the account recovery process a little bit. First of all, it's important to note that account recovery is important. Lots of users forget their passwords and they need access to their account, so we do need to implement some sort of account recovery. But it's a complex problem, so it's implemented with a complex process. So the first thing we try to do is try to send you a password reset email at your recovery email address. If you don't have a recovery email address or don't have access to that, we'll ask you, do you remember any of your last passwords, to get some signals about you. And some of the other signals we use are like the IP address from where you're running the account recovery process, as well as the browser. And then at the end of this, we'll figure out how likely is this to actually be you, and then we'll give you a questionnaire. And then if you can answer all the questions correctly, we give you a password reset. So this attack was really cool because it ran the entire account recovery process from the victim's browser. So we thought that, oh, this is really the user because he's using the same browser, same IP, and we gave him really easy questions to answer. All right. So step one for Ramses was to find an XSS on www.google.com. I'll refer to this as www from now on. Because the account recovery process starts on www, you need an XSS to be able to start it. And he found a pretty nice XSS. He found an XSS in this help tool that we have in a bunch of products, including Google Docs. The way this tool works is it has an iframe that's in red, you see over there, that is loaded in www. And then within this iframe, there's another invisible iframe, the blue one over here, which is doing the actual API communication for docs in this case to figure out what kind of help messages to show. And the way it works is with post message, the red iframe will send the blue iframe a query, and then the blue iframe will make the API call, figure out what to be displayed in the red iframe, send the red iframe HTML, and the red iframe will just insert it into its DOM. All right, sounds good. What was the bug here? Well, the bug was that the URL for the blue iframe was a URL parameter in the red iframe. So you could set the blue iframe to be on your site. So you could basically the attack works like you have this red iframe with the URL parameter pointed to attacker.com. And then you host a payload over there that sends a post message with your XSS HTML vector. And it thinks, oh, this is the help page I need to display, and it's actually your XSS. So that was the XSS he found. Let's quickly talk about the fix, because it was kind of interesting. The team asked us if it's enough to check the URL at instantiation time. That is when the iframe is created. And actually, interestingly, it's not good enough to check the URL at instantiation time. I don't know if you guys know about this, but if you create an iframe from JavaScript, you get a handle to it. You can navigate it away later. And in fact, you can even navigate iframes within that iframe. So the attack would still work if you just check the URL at the beginning, because you set it a nice URL in the beginning, and it'll pass the check, and then you wait 1 millisecond and then change it to the attacker's URL that's still fixed. So the correct fix is to verify the origin of the post message. And just, with every message sent by the blue iframe, check it came from google.com. All right, so once you have the XSS on www, you start the account recovery. So your attack is going to look like by starting the account recovery process. And to do that, all you need is the victim's email address, which is pretty simple. If you have an XSS on www, you can easily get the victim's email address. So you fill that in, and then you hit continue on this page. And obviously, in the actual attack, none of this is shown to the user. The payload for the attack is just using XSS to make the same request that would happen as if you were hitting continue on this page. All right. So when you hit continue on the first page of the account recovery process, you go through a bunch of redirects, and eventually you end up on accounts.google.com. Now, since this is a different domain, the XSS on www can't let you continue any further. And now Ramses found another low severity vulnerability that allowed him to get through this. It turns out that this, so actually let me step back a little bit. On this page, we're asking you to enter the last password you remember. And the goal of the attacker here is to click I don't know. And since it's on accounts.google.com, he can't just use the XSS he already has. But it turns out that there's something called the EST token, and that's all he needed to make this next request. This request, for some reason, didn't check cookies. It just verified it with this EST token, which was in the URL. So it was so the way the attack would work now is that you would wait until the last redirect to here, grab the EST token from the URL, the last redirect URL, send it to your server, the attacker's server, and then on the server side, you make the last request to hit I don't know, which gives you back another token called CPR, which you return back to your client-side attack, and then you continue. All right. So the next step over here is the form is asking you if you want to send a password reset email to your recovery email. And over here, the goal of the attack is to hit this link over here, verify your identity by answering multiple questions about your account. And that's easy. It's back on www.google.com. So he has his XSS and the CPR token, just can easily continue the next step. And the final step is the questionnaire itself. And since this attack was run from the victim's browser, you got some really easy questions. The first question is, when were you able to sign into your Google account last? And then the other question is, when did you create your Google account? and if this wasn't easy enough, Ramses found a page with exactly this information on it, hosted on www, which is from a deprecated app we had for moving data between Google accounts, and it had exactly the information you needed to fill this out. So the last step of the attack is just fill this out and set the recovery email address to an email address owned by you, and voila, you got to reset anybody's email account. So this was a pretty cool bug. We rewarded it pretty heavily, and the fixes, we already mentioned the fix for the XSS, then the fix for that one endpoint on accounts.google.com was to now check cookies. I don't know why it wasn't checking cookies in the past. In fact, now we've moved the entire account recovery process to accounts.google.com, and since we host less applications over there, you're hopefully less likely to find XSSs out there. So that's all we did to fix this bug. All right. Cool. That's all. Thank you. And do you have any questions?
Thank you. As Josh said, yesterday, sorry, English is not my first language, we saw increase of the report.
Yeah.
Code, yeah.
He was saying.
Yeah. We saw increase in the reports from India, so keep up the good work. And we are happy to take questions. Or there was email here, and you can reach us on that email. And any question from the audience? Please, one question at least.
Questions?
Anyone? Sure. Do you want mic?
How many vulnerabilities are still there which are not fixed yet? In a pipeline. On average, how many?
On average?
Yeah.
On Monday, it's like, I don't know. But I think on Saturdays more than on Mondays. But you know, when the vulnerability is high risk, then we even page someone to be available. We have offices around the world, so we are able to fix the really bad issues very quickly in matter of minutes, hours. And if it's not that bad, let's say days. But it was very good question, and I have some gift for you. 1 tera of the storage on Google Drive if you want. But just for 2 years. Any other question? One tera.
You have done a very big cleanup exercise in your Google Play Store, which majorly runs the Android and all the platform. All the applications which we have cleaned up, had we faced any this type of vulnerabilities which led to from those apps to your Gmail or Google account? Or another final question, recently we faced so many accounts compromised on Yahoo, which was earlier your main competitor and maybe the prime. So have you cross-checked all those stuff that it will not be again with your account, because 90% of personal email belongs to Gmail nowadays. So, and hosted with so many privacy uploads also. So what is your measures to prevent that?
Okay, so I didn't quite get the first question, but...
First question
Clean
So
up.
many cleanups of the apps of the Google Play Store.
Oh, removal. Right. Okay. Yeah. So we don't like the security team at Google is not so much into looking at third-party applications. So we only focus on applications written by Google, and those are part of our VRP. We do have a system that looks for malware on the Play Store, but we don't really look for vulnerabilities in third-party applications.
So I don't know the exact situation that you're talking about, but I do know that in the Play Store, when we discover a library that is vulnerable, we will notify the developers of an app that is affected by that in the Google Developer Console. And recently we've had cleanups where we've told developers you're running a known insecure library in your app and you have a certain amount of time to clean it up. So we give developers a chance to do right by their users and use a non-vulnerable library for a certain period of time. But I'm not aware of the recent cleanup that you're talking about, and I'd love to talk to you afterwards if you want to discuss that more.
Yeah, definitely reach to us and we can discuss it. Yeah. So last question. Hi.
Hi, this is about your zero-day bug revealing in the Windows. You work for the security team and you do the wrong stuff. I mean, I believe telling the zero-day bug is a wrong thing. How do you feel if someone do the same with Google?
So I was somehow expecting this question, and Josh is the better person to answer it.
Okay, so I think I am aware of the situation you're talking about, but so our team specifically deals with vulnerabilities that are submitted to us. So I think the question that you're talking about is how Google treats vulnerabilities that are discovered and introduced to someone else. But I can talk about the first aspect of that. So say if a security researcher comes and brings up a vulnerability to us, we ask that researcher to also tell the person who maintains the product that affects. So for example, if you were to submit a vulnerability to us that actually leveraged like an OpenSSL vulnerability, we would expect that you would tell the OpenSSL version of that too. And we would also potentially tell OpenSSL ourselves directly. So hopefully that answers your question, but if not, you can come to me afterwards and I can talk a little bit more about how we treat vulnerabilities in third-party apps that are reported to us.
So thank you. We are out of time, so thank you all and see you. We will be around if you want to discuss anything. Thank you.